In this video, we will be reviewing carbohydrates, one of the four classes of life's organic compounds. So, carbs are essentially polymers, right? And all polymers is the fact that polymers are long chain-like molecules that have these identical building blocks that add on to one another. Sort of like a train, right? We have train carts that add up to the whole train. That's exactly how polymers work. Those individual train carts are known as monomers. Right? And with the help of these monomers, we have these polymers and them creating these specialized characteristics and traits in how they're bonded to one another forms carbohydrates. Now, carbohydrates, proteins, and nucleic acids, three of the four classes of the organic compounds actually use polymers as a way to build themselves, which we'll be going over in later videos. To understand how polymers, how carbohydrates break and form, there are two big processes that we need to understand. The first being dehydration reaction. Dehydration reaction, right? Before we even visualize this, we know that dehydrate has something to do with water. And if you're speaking in the molecular scale, it has something to do with H2O. And dehydrate means not having water, right? So we know that in this process here, something needs to happen where water becomes unavailable to us. So let's draw here a polymer. So we have an OH. In biology, this is called a hydroxyl group. I think I'll have another video uploaded on functional groups, but this is something you should know. OH is a hydroxyl group. And this is covalently bonded to, let's just say, three monomers. We'll name, three monomers, A, B, and C. And this is covalently bonded to an H. This now becomes a polymer, right? There are multiple monomers in here. Now let's just say that there is another monomer here called D, bonded to a hydroxyl and a hydrogen here that wants to combine into this polymer. How would we do that? As I said, dehydration reaction simply is taking a water molecule out of the equation. We see that there's an H here and an OH. And we know that water is H2O. So what if we were to just simply take this and form a water molecule? This water molecule will serve as an exit and a direct connection between the C and the D monomers, which means that our resulting polymer would look something like this. We have a hydroxyl group bonded to four individual monomers, bonded to a hydrogen, A, B, C, D, and thus forming a bigger polymer. The exact opposite of this is actually adding a water molecule to split the bigger polymers into either monomers or just smaller polymers. And that is called hydrolysis. Handwriting's not the best, but hydrolysis, right? Let's take that big polymer that we use, right? OH, we have 1, 2, 3, 4, H, A, B, C, D. If you were to take this back to how it was, we would need to sort of break this apart, right? And we would do that by adding H2O somewhere in this equation. And what happens is, as water is added, there's a breakthrough. Now, it's important to understand that H2O is ultimately going to form into an H and an OH, right? A hydroxyl group and just an H. It is important to understand where these are going to go. You can't just place this OH with another OH, right? Because then it will not be able to do any more dehydration reactions. You cannot place this H with another H because then it won't be able to do any more dehydration reactions. You need to place the H at the end where the opposite is a hydroxyl, and you need to place the OH in an end where the opposite end is a hydrogen. So it looks something like this. OH bonded to 1, 2, 3. We have A, B, and C. And now we have a hydrogen. And then now we have the hydroxyl group here with the monomer D. And then we have an H. Right? And so if this process here, general process here, makes sense, then we can explain how some more complex carbohydrates are formed and how they're broken down. So we'll start with the most popular type of carbohydrates, and that is sugar. Essentially, all sugar is a monosaccharide. So we have monosaccharide. Monosaccharides essentially are compounds that have some multiple of CH2O. So if I was to take a compound and divide it by CH2O and it actually resulted in CH2O, then we know that it's a sugar. What do I mean by that? Let's look at glucose here. Glucose is C6H12O6. We divide this by CH2O, we know that this is a multiple, right? This was just this was just multiplied by 6 to get C6H12O6. We look at a triose sugar here. We have, C3H6O3, right? This was multiplied by 3. We have a pentose sugar, right? Pentose, as in 5. We have C5H10O5. This was multiplied by 5. And then we have hexose sugars like glucose multiplied by 6, right? Hexagon. And so that is what a monosaccharide is. Now, what happens when you combine multiple monosaccharides together? You end up getting a disaccharide. Right? We have a disaccharide here. Disaccharides are just multiple monosaccharides combined together. Monosaccharides linked by, now this is a special term, and the special type of bonding is called a glycosidic linkage. Glycosidic linkage is a covalent bond that's formed between two monosaccharides using a dehydration reaction, and that is the example I'll be showing right now. So let's look here at this example. Okay, we have here a glucose. So let me just write this here. We have here a glucose, and we have another glucose, and the end product ends up being a maltose. Right? So what happened here that caused this linkage that we call the glycosidic linkage? First, it's important to understand that when you're looking at a carbon structure, it's important to understand the nomenclature. First, second, third, fourth, fifth carbon. Right? This is the first carbon. This is the fourth carbon. This is the third, second, so on and so forth. Right? These individual ends are carbons. They're not stated here, but we have to know that there is a carbon here. So we see here that something happens in the first carbon and the fourth carbon of this for there to be this reaction. We only have an O left, which means the question doesn't tell us so, but somewhere in this process, there was an hydroxyl group taken and a hydrogen taken out of the equation to form H2O, which then left us only with an O that links these two glucose molecules together to then make a completely different molecule, maltose. This type of linkage is called a 1-to-4 glycosidic linkage. So 1-to-4 glycosidic linkage. Why is it called 1-to-4 again? Because we have the first carbon of one glucose directly linking with the fourth carbon, 1, 2, 3, 4. Fourth carbon of the other glucose molecule, thus forming a 1-to-4 glycosidic linkage. Anytime you have a question that asks about a 1-to-4 link, 1-to-3 link, just know that they're talking about the carbons of that skeleton, of that carbon skeleton.